muted.
Of our webinar is TouchPAD Programming in HMI Works using CProgramming, Part 2. This will be the second part of a three-part series where we will read I/O using Modbus RTU and do some simple controls, and we will write values back to the slave devices and explore a few other features of HMI Works. We will have an overview of the TPD and VPD series of touchpads. We will show you some features of the a complete example in C language to implement a simple control. And at the end, we will show you a small demonstration of the program using a simulator. ICP DAS was established in 1993. Our headquarters is in Hsinchu, Taiwan. ICP DAS USA was launched in 2001 to support the North and South American markets. We have over 200 R&D engineers, and we will work closely with them to add new features to our product and develop new products to support our customers. Most of our products are RoHS compliant, which means they are lead-free. We also have our ISO 9001 certification. ICP DAS has two touchpad series, the TPD series for home and building automation, and the VPD series, which was created for industrial applications. They are cost-effective solutions that can be used as HMI and controllers. The TPD series have wall boxes for easy mounting, and the VPD series also has an IP65 waterproof front panel. The sizes range from 2.8 to 7-inch touchscreens, depending on model number, and there are options for serial and Ethernet communication, including some with Power over Ethernet or PoE. The touchpads must be programmed using our HMI Works software development package. This can be downloaded free from our website, and there's no additional cost. HMI Works allows for C programming and ladder design programming using our ladder designer. In this webinar, we will focus on programming in C language. HMI Works has widgets and a graphics library to create a user-friendly HMI. The touchpads can communicate with Modbus protocol, both TCP and RTU, and connect as masters and slave devices on those. They also have the ability to communicate to our DCON protocol modules, and users can program their own protocols using C programming. In this webinar, we will be using the connection menu shown instead of the API functions to establish communication, like we did in the previous webinar. We will also be using tags as variables that are available throughout the whole project. In the previous webinar, we had two slave devices. When the touchpad was showing the information of one of the devices, it was not pulling data from the other device. This time we want to be pulling the data of all three PLCs continuously, independent of which screen the touch screen is on. We will walk through a complete programming example in C language in HMI Works, detailing all the steps. The final program will be reading 4 analog inputs from 3 PLCs, communicating by Modbus RTU. The PLCs will have IDs of 1, 2, and 3. The controls will be set using 4 analog outputs, 8 digital outputs, for each PLC. The touchpad will have a main screen that will show the general status of the 3 PLCs and the communication. Then we will add screens for each PLC separately. Let's begin. To start, open HMI Works and select the option for a new project. Then, select the touchpad type that you want to be programming for. Give the project a name without spaces and special characters, and be sure to specify the folder where you want the project saved. Depending on the touchpad that you select, you will have the option to change the orientation of the layouts, to either landscape, portrait, portrait flip, or landscape flip. And you will be able to select your default programming language, whether it be standard C or ladder. For this project, we're going to use standard C. And we're going to design for a VPD 130 touchscreen. You will get a clean project with at the left side the workspace and the toolbox. In the previous webinar, we worked mostly through the toolbox. This time we will be using both the toolbox and the workspace. With the workspace, we will be able to create connections for communication and the tags that we'll need for the project. Right-click on the connection item in the workspace and click New Connection. That's shown here directly beneath Program. For our new connection, we must select the baud rate and the parity options, make them match our COM1 settings to talk to our Modbus RTU slaves. With this new device that we're creating right afterwards, we are going to be selecting New Device. We must select the correct option for Modbus RTU Master. Here we could also select Modbus RTU Slave or Decon Slave, depending on what modules we're talking to or what slave devices we have in this case. The touchpad can also be a slave device or a master device, so you would have that option as well. From the device series, since we're going to be just using a simulator for this, we're just going to use user-defined and create a few analog input, digital inputs, and digital output tags. Note that we need to set the net ID of 1, and the timeout setting and scan time we'll just leave as the default of 200. Then we select our, actually let me go back and show you. We select Edit to add our tags. Edit is shown right here next to the connection type. And here we enter our number of DO, AO, and AI tags. For this example, we're going to be using 8 DOs, 4 analog inputs, and 4 analog outputs, and with the start address of 0 for simplicity's sake. If you did have, a different start address, you can select that, and you could also do protocol base address 0 or PLC base address 1 by using the drop-down box. Then you simply click OK, and we'll create our second and third tag, or third examples like this. But this would be the result for PLC 1, where on the right side, you'll see a list of the tags and tag names. You can change those by clicking on them and then modifying it here. The start address is shown and the IO type. There's a few additional tags that are created at the bottom. We'll be using a few of these during our presentation. The error tag will be used to show communication errors to this particular slave device. And the enable and action tags can also be used in the logic as well. Okay, once we've created our tags for PLC 1, we do similar for PLC 2 and PLC 3, and we note that the difference between them would be the node ID or Modbus ID. Let's see, for this example, we're going to assume PLC 1 has address 1, PLC 2 has address 2, and PLC 3 has address 3. And these will be the tags we'll use for our project. Okay, after that, we can create virtual tags as well. Virtual tags are used to, in this case, display alarm values, but they can also be used for mathematical operations, for changing values without affecting the value of a tag, or for, say, combined logic. Like, for instance, if you had 2 light switches which control the same light, but you only want to create an OR operation to make it so that if either of them are pressed to be on, the light will be on, and if both are off, then the light will be off. Okay, these virtual tags are created by clicking on virtual and right-clicking and selecting new virtual tag. In this example, we're going to create a PLC 01 limit alarm, and we'll create a PLC 02 and 03 limit alarm as well. Functions for the tag. As we will be working with tags, we will need some functions to get the tags to set those values. The VAR value function will return the value of the tag. The VAR set function will set the value, and the value will be passed as a parameter. The VAR set write data function will set the tag to the value, pass as a parameter, and will write it via communication to the PLC. In our example, that connection would be by Modbus RTU. On the main screen, we will show the general status of the PLCs. We will start by changing the name of the frame to main on the right side over here. At the left side, we will use the Toolbox tab on the drawing menu to create some text boxes. These text boxes we will use to create the main, the PLC 1, and then we can click on those and modify the PLC 1 to be PLC 2 and PLC 3. But in this case, we'll just copy it as shown. So the result will be this. And then you can click on each individual object. Then in the inspector on the right side, you can modify the name to PLC 2 and PLC 3. Then we will use our object list system widget to create the images for our alarms. This is done by selecting the system tag properties on the left side over here, and then selecting object list over here, and the object will appear over here on the right side. This won't be part of this what's seen at this point, so it's usually placed off the screen just to the side of the widget that's going to be associated with it. Okay, so once you click on object list, you must select the objects which are associated with it. These are the pictures that will be displayed upon or based on the I/O tag condition. Notice next to where it says controller right here, there's a 0. This will be displayed, this object will be, or this image will be displayed if the tag value is 0 associated with this object list, and the object with the 1 next to it will be displayed if the Boolean value is a 1, or logic 1. So the picture will change as the tag value changes. This is great for on-off as well as analog values as well. Like you can have more than 2 objects, like if you had, let's see, say a stoplight. There's a red light, a green light, and a yellow light. The red light could be associated with the 0 value. The 1 value could be associated with a yellow light, and the number 2 value would be associated with the green light. Okay, we will also create an object list to show the error statuses. So we will use these 2 objects shown on the screen, the button 01 and the button 02. The objects are selected from the drop-down box and they're categorized. You can also import your own images into HMIWorks and use them within the project. The end result will be something similar to this, where we will use the checkbox widget to associate with the object lists. This is done by creating selecting checkbox over here under widgets, drawing a rectangle, and then associating in the inspector on the right side with your corresponding object list. Okay, then we will place a timer on the main screen. The timer widget is shown over here under System Properties. This also is not shown or not a graphical object, so it won't be placed on the screen. Just place it just off the screen. And then you'll be able to set the timer properties. The interval is the most important. These are in milliseconds, so at this point, every 200 milliseconds, the operation inside the timer widget will be executed. Let's see, and for this one, we'll be reading the Modbus RTU data at 200 millisecond intervals. So the screen will be refreshed at the same interval, and the event handler by pressing the 3 dots on the end to execute the property of the inspector. Okay, the code for the timer event handler. Now we can start creating the code for the main screen. In the timer event handler, we will be calling the PLC routine function. This function will check the limits of the analog inputs, and depending on their values, it will set the analog outputs. If the values are in the desired range, the digital outputs or alarms will be off. Otherwise, there will be a low alarm or a high alarm. If there's any alarm for PLC 1, the PLC limit alarm will also be set to 1. We will create the code for PLC routine later, but the rest of the code in the timer event handler is to simply set the different checkboxes to either show the PLC status with limit alarm tags or the communication status with an error tag. For the function parameters, we will take a quick look at the function parameters. A parameter is a symbolic name for data that goes into a function. This data can be passed by value or by reference. Passed by value means that a copy of the data is made and stored with the name of the parameter. Any changes to the parameter have no effect on the original data in the calling function. A parameter reference refers to the original data in the calling function. Thus, any changes to the parameter are also made to the original variable. As an example, we'd like to illustrate the difference between how these parameters work. We will have two functions to add two values and give the sum of those two values. The add values wrong will receive all the parameters by value and function. Add values right will receive the values, the first two parameters by value, and the third parameter by reference. Because add values wrong is receiving all parameters by value, when the function is called with parameters and the sum, whatever is done in the function will be lost after returning from the function. So sum two values will be 5, but sum two values capitalized will be 0. In the function definition of add values right, the asterisk character indicates that sum two values, in lower cases, will have a parameter passed by reference, and this function call of add values right, the ampersand character indicates that the sum value, capitalized, is being passed by reference. In the add values right function, the parameter that is being passed by reference needs to use the asterisk before its name when used. After calling this function, the variables sum two vals will have the desired value of 5. So the difference between these two is right here, the star and the star. And let's see, where else was it? Right here. Wrong value is 0, or because of 0 there and 0 there. Okay, now let's see, checking limit function. We will create a helper function to check the values of the analog inputs. Please note that analog in is passed by value, and the rest of the parameters, low alarm, high alarm, and analog out, are passed by reference. So the changes of these parameters will be done to their original values or variables. The function checks if the analog input value is lower than 200 or higher than 800 or between the two limits. If it is lower than 200, it will turn on the low alarm and set the output to 10. If it is higher than 800, it will turn on the high alarm and set the output to 90. Otherwise, it will turn both alarms off and set the output to 50. So 200, set it to 10. Greater than 800, set it to 90. And in between, leave both alarms off and analog output value 50. Now we will get back to the code for the PLC function. We are not working with simple C variables, but HMI Works tags instead. And they need functions to get and set the values. So we can't simply call our helper function check limits with the names of the tags by value or reference. So we will create 3 auxiliary C variables called low alarm, high alarm, and analog out, all lower cases as shown, to pass the reference to check limits. The analog input parameter is passed as value, so calling the var value function with the tag name will return the value and then will be passed as a parameter to check limits. Afterwards, the digital and analog tags will be set according to the values of the variables in C using the var set write data function. The second part is to check if any of the alarms, either low or high, are turned on. To set the tag PLC 01 limits alarm to 1, otherwise it is set to 0. To complete the PLC routine, copy this function and implement it for PLC 2 and PLC 3. With this, we will finish the coding for the main screen. Then we will create a new frame called PLC. This will be renamed for the specific PLC later on once we copy it. From the drawing menu of the toolbox, we will have 10 text boxes, 8 for analog inputs and an output, 1 for the PLC status and 1 for communication status as shown. Let's see, then we will put 2 pictures, a left and right arrow to change the ID and the PLC accordingly. So in other words, it goes from PLC 1 status to PLC 2 status to PLC 3 status, and then you can also go back by pressing the back arrow. After creating the PLC frame, we go back to the main frame to put a hotspot on the right arrow. Make sure that the enabled property is true, and for the go-to property, set it to PLC. This way, by touching the arrow during runtime, the screen will change from main to PLC. We will use 9 labels from Widgets menu of the toolbox. The first label is to show during runtime the PLC ID of the information shown below. The other 8 labels are for the analog input and output values. And that's done over here under Widgets and Label. And you draw a rectangle and associate the tag associated with that. Okay, from the System menu of the toolbox, we will get 4 object lists. We will use them to store the graphic value of the high and low alarm for the PLC status and communication. For the low alarm, we will use a gray and blue button, both from the button drop-down menu. These are pre-installed graphics. Again, you can import your own objects. Simply just use Photoshop or Paint and save in the proper format shown in the manual. For the high alarm, we will show a gray button and a red button, or circle, I guess, for the LED status. For the PLC alarm, we will show these objects, either a picture of the PLC or a red X. And finally, for the communication error, we'll use our green circular checkbox or check mark and a gray X as shown. And then we'll associate the object list with the checkbox widget. So again, the alarm next to that has a picture of the PLC if the status is good. And for the COM box, we associate the appropriate object list. Let's see, then before starting the code for the PLC frame, we will create a new tag in the workspace. This virtual tag will be named PLC_IDX and will have the default value of 1. We will use this tag as the ID of the PLC, and we want to show the information on the screen. From the system menu of the toolbox, we will get a timer for the PLC frame. We'll put the interval of the timer at 200 milliseconds and then create the event handler for the onExecute property. Shown over here. Next, for the code for the main screen, we created the PLC routine function that we will use to check the limits of the analog inputs and set the analog and digital outputs. We need to set that function to execute when we are at the PLC screen. For this, we will use the extern word of C language. With the keyword, we indicate to the compiler that the function has been defined in other files, in our case, in the main screen. So we won't have to repeat the function, just call it in the file. We create a string to print the title of the screen and 8 strings for the analog input and output values. In the event handler for the timer, we will call the PLC routine to update the limits and output values. Then we will use a switch case function to select which PLC information will be shown. The parameter for the switch will be the PLC IDX tag. So depending on its value, we will execute the code in the case with that specific value. Case 1 is to show the information of PLC 1. So we will print the values of the analog inputs and outputs to the corresponding strings. Then we will set the checkboxes for the low and high alarms, and also the PLC and communication status. The break keyword is at the end of the case. Copy and paste the code of PLC 1 and adjust it for PLC 2 and PLC 3 accordingly. After the switch function, where we printed the strings for the analog input and output value, we will use the label text set function to set the strings on the screen in the label widgets. We also print the string of the title and set it to its label. This is all we need to do for the timer event handler. We use the switch case function with PLC IDX, but we haven't created a way yet to modify the value of PLC IDX. We do this by putting a hotspot on the arrow. This time we will use the on-click event handler of the hotspots, instead of the go-to frames we use on the main screen. That's shown over here in the blue. Make sure both hotspots are enabled and created with the on-click handler shown. Now we have to code the two event handlers, one for the right arrow, the other for the left arrow. For the right arrow, every time we click, we will add one to the PLC IDX. So we will use the var_set function with the current function of PLC LDX +1. We only have 3 PLCs, so when the PLC IDX is equal to 4, we set it back to 1 to show the PLC, or show the first PLC again. For the left arrow, we subtract PLC IDX. If the PLC IDX is equal to 0, we go back to the main screen. Let's see, instead of using 3 PLCs, in this case we're going to use a Modbus simulator called Modbus RTU. Let's see, we will use a USB converter instead of the PLCs, and this will just simply convert the communication signal from the RS-485 port to a USB port on the PLC for the simulator, recognized as COM ports. Mod RSM is shown here. We simply select the communication type and we set the values of the special feature of RSM to set the registers for each station. We get this feature by clicking the second icon from the right on top of Mod RSM. The standard operation of Mod RSM is to simulate multiple PLCs. All of them will have the same data in their registers. By using the separate sets, we can have different data for the different PLCs that we will need to simulate. We can create 3 PLCs with 20 registers for each PLC. With the separate set enabled, we will have PLC 1 starting the input at address 30,021. Double-click on that register. It will show station 1. Same as PLC 1. The register is 30,001. PLC 2 will have the starting input registers at 30,041. Double-click on that register. It will show station number 2. And this will be the same as PLC 2's register 30,001. And likewise for a PLC 3. In the normal operation, we will have all analog input values higher than 200 and lower than 800. The main screen will show the controller icons and showing that there is no value out of limits and the OK button for the communication. The 3 yellow boxes at the bottom of Mod RSM indicate that the touchpad is polling the 3 devices. Because we have all analog inputs in the desired range, all the digital outputs are 0, so there are no active alarms. That's shown here, over here. Similarly, all the analog output values are all 50 as we programmed in the check limit function, as shown here. And the error communication we can simulate that the PLC is offline by clicking the ID at the bottom of the Mod RSM. If we disable ID 2, we will show the communication error as shown on the screen. And that's done by this red box down here. It changes from green to red, showing offline status. In this slide, we will change the values of PLC 1 and PLC 3 to 111 and 999, as shown here and here. And we can put 2 values out of range and we will generate a low limit alarm and a high level alarm as shown here. If analog output is 10 and analog output is 90 for the alarm, or I'm sorry, analog output value will generate an alarm as shown here. Pressing the right arrow on the main screen will show the details of the specific screen for PLC 1. We changed the input values in Mod RSM from PLC 1 to 222, 111, 999, and 555, and see those values on the screen along with the correct values for the alarm outputs and communication status. The yellow box at the bottom of Mod RSM shows that all three devices are being polled properly. We can see the correct values for PLC 3 as well. Okay, in this webinar we created an example where the touchpad is polling all the devices all the time, independent of which screen is being shown. When working with devices that have similar input and outputs, we can use a single screen to show their values and use an index to decide which values to show. Otherwise, we would have to create 3 different screens with similar information. And adding more devices would mean much more work. At the main screen, we could put hotspots on the status indicators so that, for example, if there is an error at PLC 3 and it is showing on the main screen, we can press and jump directly to the screen for PLC 3. The simulator used in this demo was Mod RSM, has more interesting features that we can use for testing and developing communication and modify the program based on the device. Let's see, we have finished the webinar for today. If you have any questions, please feel free to type them in the chat box, or you can email us at or call us at the phone number shown and the email address shown.